As we continue our journey toward understanding optimization, we're going to have to learn an analytic approach to determining where our graphs are both increasing and decreasing and where they're concave up and concave down. So that's where we are landing today in section 4.5. We discussed the mean value theorem during our last class, and our mean value theorem has some direct correlations to determining where our function is increasing and decreasing. So if we look at the definition here in the pink box, we see that if f is continuous over a closed interval from a to b and differentiable over the open interval from a to b, then if f prime of x, the derivative, is positive, greater than 0, for all x in that open interval from a to b, then f is increasing over a to b. If f prime of x is less than 0 for all x in our interval, then f is decreasing over that interval. So how does this come about from the mean value theorem? So remember that when we had a function that started at a and went to b, and we looked at the slope of its secant line, means that somewhere along the way in that interval, we also had the slope of a tangent line that was parallel to that secant line. And if you notice here, to move from a to b, from our mean value theorem, to move from a to b, our graph went up and to the right, and indeed is increasing. The same can be said of a function that is decreasing. If we look at our slope of our secant line here, it's a negative. Slope of our tangent line would also be negative. This is down and to the right and decreasing. So there is a direct result. This is a direct result of the mean value theorem. As we saw in a previous section, we talked about what happens when our graph switches from increasing to decreasing and decreasing to increasing. We called those a local extremum at each point, or if we have multiple local extrema. So we said when f switches from increasing to decreasing at x equals c1, some point, f has a local maximum at c1 f of c1. And likewise, if f has a local minimum at c2 f of c2 when f switches from decreasing to increasing at x equals c2. And we call these special places critical points. So we've already talked about critical points, and we've already talked about local maxes and mins. We've talked about increasing and decreasing in section 4.3. But now we're going to find an analytic approach to find them. So are all of our critical points guaranteed to provide us with a local extremum? And if you remember, the answer is no, because sometimes critical points are found where the slope of our tangent line is undefined, which means that we either have a sharp peak, a sharp trough, or we have a piecewise function, or we have, you probably guessed it by now, a vertical asymptote. So not all critical points provide a local extremum. So no, not all critical points provide a local extremum. Let's see your extremum. There we go. So if we consider the graph of g of x equals x cubed, we consider that function, we'll start there. As we learned in section 4.3, we can find any possible critical points by setting g prime of x to 0 and solving for x to determine what values of x show us where f prime of x is either 0 or undefined. So let's consider doing that here. Let's look at g prime, let's look at g of x. If g of x is x cubed, g prime of x by the power rule is 3x squared. And then we want to know, where does 3x squared equal 0, or where is it undefined? So we'll say 3x squared equals 0. Well, that's only when x equals 0. It's never undefined, right? So g prime of x is never undefined. And remember, we often have undefined points of x when we divide by 0, when we take the square root of a negative number, when we have an asymptote, when we have a jump discontinuity. Those are the places where we would have a g prime that is undefined. So what does our graph of g of x look like? Well, if you remember what a cubic looks like, we're looking at a basic cubic here, and I'll try to do my best to draw it fairly well. We have a cubic that looks kind of like this. So our only extreme point here, our only critical point is right here at x equals 0. That's our critical point. Now, is it truly an extreme point? Does it provide us with a local extremum? And the answer is no. No, this is not this critical point, this is not an extremum. And why is that? Because we don't switch from increasing to decreasing or decreasing to increasing. In fact, we're increasing to 0 and we're increasing after. You'll notice we're increasing up to 0 and then we're continuing to increase. So remember, this is one of those special functions we talked about that sort of levels out momentarily at x equals 0 and then continues on with its business. So here we would say, we'll just even put it in because g of x is increasing on negative infinity to 0 and 0 to infinity. It doesn't change direction. So in that case, do you think that all critical points are guaranteed to provide a local extremum? The answer is no, they are not. If you want to look at a little bit more evidence for this one, we saw this in Lab 6, and we saw some of it on the Unit 2 review. As a follow-up to our last question, let's look at this graph that I pulled from the textbook. First of all, I need to let you know that there was a typo on the far right side where it said f prime of x was greater than 0 there. It's truly less because it is decreasing. So the newer version of the open source text probably has fixed this by now, but I wanted to let you know there was a typo in it in the PDF version that is posted on Blackboard. Let's see if we can determine where our function has critical points. That's question A. Where are the critical points? So remember, this is where f prime of x here is equal to 0 or f prime of x is undefined. So let's see if we can figure it out. If you'll notice, we have f prime of a is undefined, and look at what that one looks like. It looks like a spike. So if you think about it, these slopes are getting larger and larger and larger and larger until they become vertical from the left, and the slopes are also becoming more and more and more vertical from the right. So our derivative at a would be undefined because the slope is undefined. So that's where we have an undefined derivative. We'll notice that we bottom out at b, right? We switch from decreasing to increasing, so we have a 0 sloped tangent line there. And then we switch from increasing still to increasing like we did with our x cubed at c, but it does flatten out momentarily at c. And then at d, we also have a spot where our function has a 0 slope. The derivative has a 0 slope. So what do we find then? That we have critical points at x equals a, b, c, and d. So we have critical points at all of them, but are all of them extrema? The answer is no, because here we have no extremum at a. Well, let's see if B, C, and D are. Well, we already said C is not because we just looked at one like that. We can probably visually tell that at B we do have a local min because we looked at all of the analysis of the graph before we learned how to solve for these points. So we know then that at D we have a local max. The other parts of this question are where's our function increasing and where is it decreasing? So if we look at where our function is increasing, well, we're increasing from negative infinity up to A. And then we switch to decreasing. We go back to increasing from B to C, and then again from C to D, just like we did with G of X, and then we switch back to decreasing. So let's write out where the intervals in which our function is increasing and decreasing. So we'll color code it. Our increasing, which we highlighted in purple, is from negative infinity to A, again from B to C, and again from C to D. Our function is then decreasing everywhere else, which is from A to B, and again from D to infinity. So it's only decreasing on those two intervals. And I know that we have labeled on the graph itself what our extrema are, but let's look and see if we can write them out as a list. So we said at x equals A, we have no extremum. At x equals B, we had a local min. At x equals C, we had no extremum because that was where our graph looked like the g of x did before of x cubed. It increased, it momentarily flattened out, and then kept on increasing. And x equals D gave us a local max. In fact, we could call this one a global max as well. Everything that we've looked at so far can be summarized with something we call the first derivative test. And it says, suppose that f is a continuous function over an interval I containing the critical point C. If f is differentiable over I, except possibly at C, then f of C satisfies one of the following. If f prime changes sign from positive when x is less than C to negative when x is greater than C, then f of C is a local maximum. And that makes sense if you think about it, because it means if you look at your number line, at C to the left of C, it changes from positive to negative, f prime does, which means our function goes from increasing to decreasing. So you can see at the top we would have to have a maximum. If f prime changes sign from negative when x is less than C to positive when x is less than C, then it has a local minimum. And this is by the same line of thinking. So when x is less than C, we have negative and decreasing. And then we have, to the right of it, we have positive and increasing, which definitely gives us a min, even visually. The last one says if f prime has the same sign on both sides of C, then f of C is neither a local max nor a local min. And that's what we saw when we were looking at our g of x being x cubed. It means that at C we have something like it's positive, it hits C, and then it goes back to being positive. So it looks like this. Or we may have one where it's negative and decreasing, and then hit C where it's momentarily zero, and then it's negative again and decreasing. So it makes sense that these two would have no max or min, no extremum. So let's see if we can figure out how to do all of this on our own. The catch is we have an easier way to do this. What I just drew for you are a bunch of sign charts. So we are going to use sign charts to help us here. So we're going to use sign charts to determine increasing and decreasing, and maxes and mins. Right? So let's see how this is going to work. I'm going to leave the theorem at the top there for you to see. And let's look at example 4.5.2, which says that use the first derivative test to find the local maxes and mins for the function f of x equals x cubed minus 3x squared minus 9x minus 1. First things first, we have to find our derivative, which is going to be by the power rule 3x squared minus 6x and minus 9. And remember, we want to know where this function is either undefined or equal to 0. Well, this is a polynomial, and it has no points of discontinuity, so it's defined for all x, so we don't have to worry about undefined. So let's focus on seeing where it's equal to 0. So we'll factor out a 3, and then we've got x squared minus 2x minus 3. Well, what multiplies to give us negative 3 and adds to give us negative 2 would be negative 3 and positive 1. So x minus 3, x plus 1. So here, 3 is never going to be 0, so we don't have to worry about 3. But x minus 3 could be 0, or x plus 1 could be 0, and our statement would be true. So x here could be 3 or negative 1. So these are our critical points, I should say. X equals 3 and x equals negative 1, which makes them our possible extrema. So I've started our number line here. Let's do f prime of x. And when we look at our number line, we're looking at intervals. And what we're interested in is going from negative infinity to our lowest critical point, which is negative 1. Then between negative 1 and our next critical point, 3. And between 3 then and positive infinity. Those are our only intervals of interest. So now what we have to do is we have to figure out what's happening in each of these intervals. So if we were to look at negative infinity to negative 1, that would be like asking about, let's say, negative 3. So if I think about negative 3 and I look at f prime of x, so we always label our number line with the function we are evaluating. Here we are evaluating the first derivative. So if we found f prime of 3, for instance, let's see, that would be 3, and I'm using this form, 3 times negative 3 minus 3 times negative 3 plus 1. Or the way I like to think of this is a positive times a negative, and then negative 3 plus 1 is also a negative. So I have positive, negative, negative, which is going to be a positive. So in that interval from negative infinity to negative 1, our derivative is positive, which means our function is increasing. If we switch to decreasing between negative 1 and 3, then we have a maximum at x equals negative 1. And I will say this, and I'll repeat myself a lot of times on this fact. The easiest points to test are always negative 1, 0, and 1. In this case, we couldn't use negative 1 because it is a critical point, so I just picked a number slightly less than negative 1. Now, when we switch from a negative to a positive, those numbers always have to go through 0. So when you have critical points where 1 is negative and 1 is positive, if 0 is not also a critical point, then test 0 because it makes your life so much easier. So if we tested 0 and we found f prime of 0, we would have that positive 3 again times 0 minus 3 is going to be negative, and 0 plus 1 is going to be a positive. So if two positives times a negative, which is going to be a negative. So our first derivative is negative, which means that our function is decreasing. And we just found a local max at x equals negative 1 because our function changes from increasing to decreasing at x equals negative 1. And then let's test one last point in the interval from 3 to infinity, like, I don't know, 5. Let's try 5. We get 3, which is positive, times 5 minus 3 is 2, which is positive, and 5 plus 1 is going to be positive. So it's all positive, which means our function itself is increasing. And now you'll notice we have a local min because we switched from decreasing to increasing at x equals 3. So we'll need to summarize what we found. So we say f of x has a local min. Well, here, we'll do the local max first. Has a local max at -1, f of -1. And f of x has a local min at 3, f of 3. And we could actually find f of -1 and f of 3, but I'm not worried about that too much on this problem yet. We'll get to that. We'll start plugging in points later. But let's try another one. Let's look at part B, which I still have labeled part A there again, sorry. So if we look at part B, it says h of x is 5x to the 1/3 minus x to the 5/3. So for this one, I certainly upped the ante because now we have a fractional exponent on both terms, which means now we're looking at two rational functions, right? Rational, fractional. So we have two roots here. So this is 5 times the cubed root of x minus the cubed root of x to the 5th. So let's take its derivative and see where that leaves us. So h prime of x is, by the power rule and the constant multiple, 1/3 times 5 is 5/3. X to the 1/3 minus 1 is -2/3. Minus by the power rule again, 5/3 x to the 5/3 minus 1, which would be 3/3, so it leaves us with an x to the +2/3. And this is where we need to figure out how to solve for 0. So we have 0 equals 5/3 x to the -2/3 minus 5/3 x to the 2/3. And we could just go ahead and factor out that 5/3. So let's do that. Instead of writing it this way, we'll write it as 5/3 times the quantity x minus 2/3 minus x to the 2/3. So x to the minus 2/3 minus x to the 2/3. Well, 5/3 is never going to be 0, so we don't have to worry about that. But now we have 1 over x to the 2/3 equaling x to the 2/3 over 1. And so here now we can multiply both sides by x to the 2/3. So we end up with 1 equaling x to the 4/3. So the only time that x is going to be, x to the 4/3, sorry, is going to be 1 is when x is positive or -1. And how do we know it's a positive or negative? Well, if you think back to when you learned about rational exponents, we have to raise each side to the reciprocal power, which will be 3 over 4. The 3's and 4's will cancel out, but because the reciprocal power has a 4th root in the denominator, we really have that the absolute value of x is now equal to 1, which means x is plus or minus 1. We also know here that our derivative, f prime of x, oops, sorry, this is h. H prime of x is undefined where? Well, that's where we would maybe divide by 0. Well, if you remember, at one point we had 5/3 x to the -2/3, right? So we have an x to the -2/3, or a 1 over x to the 2/3, which means that x cannot be 0. So we have critical points where x is plus or minus 1 and h prime of x is undefined at x equals 0. So when we do our number line now, we're going to need to use -1, 0, and +1. So let's draw our number line. And this one's just going to have a lot more on it. So we'll have, here's our h prime of x, and we've got -1. This goes down to negative infinity. We have 0, and we have 1, and it goes on off to positive infinity. So when we check our values now, let's see what we get. So we check a number less than -1, like -2. Then we will end up with, let's see here, I'll put it in for you, f prime of -2. You can plug this into your calculator if you like. We find out that it is negative. And so our function is decreasing from negative infinity to -1. And then if we find a number between -1 and 0, like -1/2, oh, I wrote f again, let's make this h. H prime of -1/2 is now positive. And so we have a function that is increasing from -1 to 0. At 0, our function is undefined. So there's a good chance that we don't know exactly what's going to happen to the right of 0. It could continue to increase. It could switch to decreasing, but still be undefined. We're not really sure. So let's figure out what happens here. If we find h of 1/2, because it's between 0 and 1, we find out that h prime, of 1/2 is still positive, and so our function is continuing to increase after the point at which it was undefined. And then our remaining interval is from 1 to infinity, so let's look at h prime of 2. And in that case, we're going to have a negative value. And so that means our function turns around and starts decreasing again. So remember, we have a local min where our derivative switches from negative to positive, and we have a local max where our derivative switches from positive to negative, because it means our function is switching from decreasing to increasing or increasing to decreasing respectively. So we have a local min at x equals -1 and a local max at x equals 1. And you notice that there's no extremum at x equals 0. So we'll organize our thoughts down here. We'll say that h of x has a local min at -1, f of -1. H of x has a local max at, well, we said that was at 1, f of 1. And then the last one to say is that h of x has no extremum at 0, f of 0. And this is how we're going to look at increasing, decreasing, local maxes, and local mins from here on out. Previously in section 4.3, we discussed what it looks like visually for a function to be concave up or concave down, and we discussed the point at which it switches is called an inflection point. So just as we had an analytic approach to finding critical points, now we need an analytic approach to finding possible inflection points. And that's where we have our test for concavity. If we let f be a function that is twice differentiable over an interval I, then if our second derivative is positive for all values of x in that interval, then f is concave up. So if our second derivative is positive, then our function is concave up. If our second derivative is negative on that interval, our function f is concave down. So even a little easier to remember than our increasing and decreasing. So we're going to look at a couple of functions here and see if we can figure out, for this one, for example 4.5.3, let's figure out where our function is increasing and decreasing, has any local extrema, and its concavity. And then we're going to try to determine if we can see a relationship between our local extrema and our concavity. So let's start with finding our derivative, because we need to know that to figure out where a function is increasing and decreasing and has any local extrema. So let's start there. So f prime of x here. Well, if f of x is x to the fifth minus 5x cubed, power rule makes quick work of our derivative, which would be 5x to the fourth minus 3 times 5 is 15, x to the 2. We'll set it equal to 0, and let's factor out what's common, which would be a 5 and an x squared, which means we're left with an x squared minus 3. So here, if we set either one to 0, we get 5x squared equals 0, which means that x is 0. If we set x squared minus 3 to 0, that means x is now plus or minus the square root of 3. So we have 3 possible extrema. So those are our critical points. We also then need to find our second derivative. So let's do that. Well, remember, our second derivative means take the derivative of the first derivative. So if our first derivative is 5x to the fourth minus 15x squared, enter the constant multiple rule, sum and addition rule, and that good old power rule one more time. 4 times 5 is 20, so 20x cubed, minus 15 times 2 is 30, and x to the 2 minus 1 is x. So when we set this one equal to 0, we'll factor out what's common, which would be a 10 and an x, and we're left with 2x squared minus 3. So we would have 10x equals 0, so x is 0. And then we would have 2x squared minus 3 equals 0. So x would be plus or minus the square root of 3 halves. So we now have plus or minus the root of 3 as possible critical points, or sorry, as possible extrema, they are critical points. And now we have some possible inflection points at plus or minus the root of 3 over 2 and 0. So step 3 is going to be drop it all on a number line. All right, let's draw our number line here. And as you might have guessed, we're going to need 2 different number lines. So let's do one for our first derivative, and we'll do one for our second derivative. So for our first derivative, f prime of x here, we need to test from negative infinity to, let's see here, negative root 3. Then we have negative root 3 to 0, 0 to positive root 3, and then positive root 3 to positive infinity. So if we were to test out points in between, if you think of a number less than the negative root of 3, so say for instance negative 4, negative 2 even, 5 times x squared is always going to be positive, so that's going to be a positive. And if we think about a number like for instance negative 2 squared, well negative 2 squared, and we are by the way plugging into this version, negative 2 squared is going to be 4. 4 minus 3 is still 1, which is positive. So we have a function that is increasing from negative infinity to negative root 3. If we choose a value between negative root 3 and 0, like negative 1, we would have 5 times anything squared is still going to be positive. It's always going to be positive. But negative 1 squared is 1. 1 minus 3 is going to be negative. So our function is decreasing from negative root 3 to 0. If we do something similar and plug in 1, we're going to have positive and negative again. So we'll still have a decreasing function. And then if we plug in a number larger than the positive root of 3, like say 2, well, we have positive times, well, 2 squared is 4, 4 minus 3 is 1, so still positive. So our function is increasing. So f of x is increasing on. Well, where do we have all those positives? Negative infinity to negative root 3, and positive root 3 to infinity. F of x is then decreasing everywhere else, which would be on negative root 3 to 0, or 0 to positive root 3. Well, we didn't label any maxes or mins, but when we switch from increasing to decreasing, we know we have a local max. When we have decreasing to increasing, we know we have a local min. So F has a local max at negative root 3, F of negative root 3. F has a local min at positive root 3, F of positive root 3. Well, what happened at 0? The answer again here would be no extremum. So F has no extremum at 0, F of 0. All right, that's everything we can get from the first derivative. Now let's take a look at the second derivative. So that one has critical points, or sorry, not critical points, but possible inflection points, and I realize I wrote it wrong up here. We forgot the halves. Plus or minus the root of 3 halves. We'll just divide that guy by 2. There we go. So we've got a root of 3 halves and a negative root of 3 halves to throw in here. So negative root of 3 halves here, a positive root of 3 halves here. And we again have x equals 0. So 0 is in here again. And then the rest of it is positive and negative infinity. So now we need to check points on our second derivative. If we plug in a value less than the root of, the negative root of 3 halves, like say negative 2. 10 times a negative 2 is going to be negative. And then negative 2 squared is going to be 4 times 2, which is 8, minus 3, which is 5. That's a positive. So we have a negative. And if our second derivative is negative, our function f of x is concave down. If we try a value in between negative root 3 over 2 and 0, like say 1, negative 1, then we would end up with a negative times a negative, which means our function switches to being concave up. If we do the same thing for the positive one, we'll end up with a positive times a negative, and we'll end up with it moving back to concave down. And for the last part, if we tried something larger than the positive root of root 3, or so the positive root of 3 over 2, like say 4, then we're going to end up with a positive times a positive. And I am using this form, this factored form. So we end up with positive again. So let's start by saying, where is our function concave up and concave down? So we would say here, f of x is concave up on, well, let's see here, that's anywhere where we have a positive second derivative, so negative root of 3 halves to 0. And it's also positive and concave up again from positive root of 3 halves to infinity. F of x then is concave down on negative infinity to negative root 3 halves and 0 to the positive root of 3 halves. And remember what we said about an inflection point. It is any point at which the concavity changes. And you'll notice here that at all the zeros for a second derivative, our concavity changed. So f of x has inflection points at x equals plus or minus root 3 over 2 and 0. They're all inflection points. And that was something that we really wanted to know. If we wanted to try to graph this function, and I will do my best to help you out here, it's not going to be beautiful, but I can try. We would have something along the lines of, moving my ruler, give me 1 second. Just going to draw you some axes. Okay. It would look a bit like something that comes down to 0 here, and it is decreasing into it and after it. So it changes concavity, so it's concave up before it, but concave down after it. So we know we have this much, and it will switch then to concave up because that's an inflection point, and then it will have a minimum and come back up. So we have an inflection point here, we have a critical point up there, critical point here, and then to the left of negative root 3 over 2, we have it switching concavity to down, and we have a maximum. So here, let's label a few of these. Here's our local max, and that is a critical point. That would be at negative root 3. I'll remember our local min here. That's also a critical point. That was out at positive root 3. And remember, our inflection points came in at 0, negative root 3 over 2, and root 3 over 2. So negative root 3 over 2, and this one would be positive root 3 over 2. So all of it goes together to help us graph our function. If you'll notice, there's actually something really interesting here. When our function is concave up, it's only possible here to have a local min. And when our function is concave down, we could only have a local max. This is not an accident. This is actually something we're going to call the second derivative test, which we're going to look at on the next page. What does this second derivative test then tell us? It says, suppose that f prime of c is 0, meaning we have a critical point, and f double prime is continuous over an interval that contains the critical point c. Then, if our second derivative is positive, meaning concave up, then our function has a local minimum. Well, that makes sense. And if f double prime of 0, our second derivative, is less than 0, then f has a local maximum. And again, that makes sense because that's concave down. You can't have a function that's increasing and then decreasing and tell me that you have a minimum because it's getting higher, it momentarily stops increasing or decreasing, and then it gets lower. That is a definition of a peak. That is a maximum. If we have a critical point and our second derivative is also 0 there, then our test is inconclusive. Let's try putting all of this together and see if we can find all of our maxes and mins and confirm it with our second derivative test. So let's look at another function here where we've got f of x is x cubed minus 3x squared minus 18x. First things first, find f prime of x. Here, f prime of x, using our good old power rule, is 3x squared minus 3 halves times 2x makes it 3x, and then minus 18. When we set this one equal to 0, we can factor out the 3. We have x squared minus x minus 6. So it multiplies to give us negative 6, and adds to give us negative 1. Well, that would be minus 3 and plus 2. So here, our critical points, well, 3 is never going to be 0, so we don't have to worry about that. x minus 3 will be 0, or x plus 2 then has to be 0. So x is either negative 3 or, positive 3 or negative 2. So there are our critical points. And our second derivative test then says we need to find now the second derivative and evaluate it at those points. So let's figure out where f double prime of x is 0. So f double prime of x is the derivative of the first derivative. So 3 times 2 is 6, so 6x minus 3. When we set this one equal to 0, we get 3 times 2x minus 1. Well, 3 is never going to be 0, so 2x minus 1 needs to be 0, which means that x is 1/2. So our only possible inflection point is 1/2. So what we want to do, if we want to do this without drawing the number lines, is we're going to use a second derivative test that says now, where is my second derivative positive or negative? Well, here's the best part is we've got critical points at x equals 3 and negative 2. So we're going to test those points in our second derivative. So this step 3 is a little different and it allows us to find these values without having to use number lines. So we have critical points at x equals 3 and negative 2. So let's try x equals 3 and see what happens. F double prime of 3 is then 6 times 3 minus 3, or 18 minus 3, which is 15. So we are concave up there, which means that x equals 3, right? So f is concave up. So therefore, x equals 3 is a minimum. If we test x equals negative 2, f double prime of negative 2 is going to be 6 times negative 2 minus 3, or negative 12 minus 3, which is going to give us a negative 15, which means we are concave down. So f is now concave down, therefore x equals negative 2 is a maximum. So we could go through all of that same information about where a function is increasing and decreasing, has any local extrema in its concavity, or if I only asked where it has the extremes, we now know where the maxes and mins are. So if we still want to know where it is positive and negative in terms of increasing and decreasing, we can do that. So if we look at our number line here, and this will also help us see both approaches together to finding any local extrema. So if we look at f prime of x, we know we have a negative 2 and we have a 3. If we plot points that are between or evaluate at points less than negative 2, between negative 2 and 3, which, reminder, that's 0, and greater than 3, we find that we've got positive value here, a negative value here, and a positive value here. So our function is increasing, then decreasing, then increasing. And hopefully that matches what we found before, where we said x equals negative 2 is a maximum. Well, we agree with that. And x equals 3 is a minimum. So now we know f of x is increasing then on negative infinity to negative 2, and again from 3 to infinity. We know that f is decreasing then on negative 2 to 3. So let's look at our second derivative then. If we look at that number line, we find out that we have x equals 1/2 as our only possible inflection point. If we test values less than 1/2, we end up with negatives, so concave down. And To the right of 1/2, we have it being positive, which will be concave up. So it is indeed an inflection point. And if you'll notice, this graphic, if you think about it, this would have to go up, come back down, and turn around. So this says it goes up, comes down, and it turns around. So it makes sense. They match. So now we can also then extend to say that f of x is concave up on 1/2 to infinity. F of x is concave down on negative infinity to 1/2. F has an inflection point at 1/2, f of 1/2. And we already said x equals 3 is a minimum, x equals -2 is a maximum. And I think that was everything that we were asked, because there's our increasing and decreasing.